Okay, thank you. Well, welcome to my talk here. The title of the talk is To the Moon and Back, Software-Defined Radio and High-Power Transmissions, and the subtitle is How to Do Cool Things and Stay Legal. My name is Marcus, and DL8RDS is my call sign. We were having a little stand down there, and we noticed many people with a call sign. So let me please first ask you, how many people of you have a call sign? Wow. Wow, okay, fantastic. Well, I expected about 5 or 10, but not so many. Okay, so then most of you have at least kind of an insight from your own practical hobby, from your own doing. Well, then let's start. The call sign is actually something that's important exactly here, up there, because this wonderful little device transmits about 10 milliwatts. And okay, the licensed people among you know how far you can get with 10 milliwatts, but a question to the others who don't have a license: how far do you get with 10 milliwatts? Let's say on short wave, what do you think? Give me guesses. Give me some numbers. Kilometers.
A few hundred?
1,000?
What's your antenna?
Yeah, that's an important point. Very important point. So the next talk will be from Michael, and Michael will present a little device, little Raspberry, with just a wire attached to it, and he threw the wire out of the window down there, and he was able to bridge a few hundred kilometers over to England just with this little wire attached to a Raspberry. So Raspberry does 10 milliwatts, so it's worth thinking about how far you can get with small power. And actually, what's so interesting about moonbounds is that all those aspects, high power and low power, comes very close together, even though they're completely different and they require completely different approaches. So now let's start. That's a nice array. It's not mine. What does it take? It takes a very, very good antenna to go to the moon. Very good antenna. The moon is somewhere between 405,000 and 330,000 kilometers away. It's quite a distance. Let's take 400,000 kilometers in that case, and you have the way back. So that's 800,000 kilometers. And that also brought me to the idea, well, was Apollo really on the moon? And from well, thinking about what is possible, what is not, clearly it was possible, and it is possible. And the guys who do that, my friends, they told me that actually you can stand on the moon with a 20-watt transmitter and transmit to the Earth, and somebody on the Earth will hear you. That is possible. What's so problematic about moonbounds is that the moon is a very bad reflector. The moon has a very uneven surface, and it is round, which means the waves come up here. Maybe there is a little mountain, and the wave will be deflected over here. And even if the moon is even here, the wave comes here, but it will be deflected somewhere else. So just a very small portion of the power that really hits the moon. I mean, you don't put all the power on the moon because the antenna is usually not so narrow. You go beyond the moon, and just a very small portion of the power will be reflected. And the science about it is, first of all, how to put as much power as you can on the moon, and how to pick up as much power as you can from the little amount of power that's going back. That's also somebody who has quite an array in his garden. There is also something about antennas, because antennas have a certain gain. The funny thing about amateur radio is that we are kind of limited in the amount of power that comes out here. But the limitation is kind of relative, because depending on the country, can put out here a power of 1000 watts legally. And that's the funny thing about it. But it gets even funnier because everybody of you has been playing around with magnifying glasses. You can of course of course concentrate all the power to a certain spot, and this is what a good antenna does. So if you have an antenna that focuses everything into one direction and produces a very, very small beam, you can make sure that all of your power really goes where you want to have it. And this is kind of a device like that. But this is also possible. That's kind of, yeah, it's mobile operation over the moon. The antenna is a 2-meter antenna. It's about 10 meters long, and that also works. I've been talking quite a lot about antennas. Obviously, antennas play an important, a very crucial, very, very, very important role. And I take the jump from the antenna to filters, because in the morning Tom told us that an antenna is eventually a filter. When you have power distributed over a spectrum, that's the frequency, that's the power. If it's evenly distributed, now let's take a higher power level, evenly distributed, and you have an antenna has a resonance, and it will only pick up what's in this resonance bulb. Like, well, if this is the resonance, then this is what it picks up. And of course you want to make sure that it picks up as much as it can. But there is something else that's important about software-defined radio and reality. That's the question about the dynamics of the analog digital converter, which means if you have background, all kinds of transmitters, LTE base stations, broadcast transmitters, everything, all of that energy will come into your receiver. All of that energy will go in, and the ADC sees, okay, there is an amplitude. It samples the amplitude at a certain point of time, no matter what kind of frequency that is, first of all. Later on, you can tell, okay, you can calculate it out, but it's that's the reason why it's very important to, well, for example, this is what the antenna picks up, and this is the frequency which you really want to hear. And if there is a strong signal about here, the antenna will also pick it up. But what comes into the line will be the energy of both signals. And the big signal that's up here will eventually reduce the sensitivity of your receiver, so that you cannot pick up the very, very weak signal which you really want to hear. And that's the reason why it's very reasonable to put a filter, a narrow filter here, so that you blank out all the rest which you don't want to hear, and this is what you put into your ADC. Now let's have a look at the link budget, how to calculate that. 1 milliwatt is 0 dBm. It's a logarithmic scale, as we heard several times this day. 1 watt is 30 dBm. 1 kilowatt is 60 dBm. In Germany, we have a maximum legal limit of 750, which is a few dBms less, but after all, the dBms here, I mean, since the antenna focuses it, you can't really tell it's a 1000 watt signal from a 750 watt signal. That's just a little weaker or stronger, but that's not really the point. Let's calculate the round. Let's take the round figures because it's easier to calculate. If you have a good Yagi antenna on 2 meters, on the 2 meter band, 144 megahertz, you will have about 14 dBd or dBi. dBi is referring to the radiation to a ball that radiates in all directions, but it doesn't exist in reality because an oscillation always happens between 2 points, and it disturbs the idea, or that crashes your idea that it transmits into all directions. So after all, the isotrophic body does not exist in reality. It's just a theoretical measure. So anyway, if you have a 14 dB antenna, dBi antenna, and if you take 2 of these antennas, you gain 3 decibel. And if you take 4 antennas, you gain another 3 decibel. And after all, you will end up at 20 decibel gain. This is the gain which you can add to your transmission power, because it is practically the concentration of your signal into the direction which you want to have. So what comes out in front of your antenna is 80 dBm, which is 100 kilowatts, and it is more or less legal. I mean, if we have 750 watts in Germany, so you have to deduct a little bit, but that's not the big portion. In America, the legal limits are, I think, 1.5 kilowatts, so even a little more. So 100 kilowatts is completely legal. But this example refers to the 2-meter band and not to the antenna here. Because this antenna very, very likely has a gain of 40 to 50 decibel. So you have to add 50 decibel instead of the 20 decibel. At home in my experimentation site, we have a dish of 3 meters diameter, and we have a crazy idea. It's called the chicken project. That's the idea of roasting a chicken at 100 meters distance. We haven't tried it out yet. Okay, but that's for the calculation. In front of the antenna, that's the ERP. You come out with 100 kilowatts, and then you send your energy to the moon. The way to the moon is quite easy still, but the reflection is the problem. So the path attenuation overall at about 140 megahertz is 250 decibels. This is what you have to deduct. That's why I have a minus in front. And this is what comes out, 170. This is the signal strength that comes back to the Earth, the signal strength in front of your antenna. And now the antenna helps you again, because since it is 20 dB, has an according focusing power, it gives you 20 decibels. That's the antenna gain. And then you, in this case, in these applications, you usually have a preamplifier. So wonderful devices with a PHEMT transistor, a very low noise transistor, fantastic things, fantastic devices. And after all, you end up at minus 130 dBm. And then you have a trick, because it always depends on the breadth of the signal. If you have a very broad signal or a very narrow signal, that helps you also quite a lot. Here in this case, I'm talking about 10 decibel, but this varies very much according to the kind of, well, how you use and how you decode the signal which you want to hear afterwards. In this case, we end up at minus 120. This is 1 watt, milliwatt, microwatt, nanowatt, picowatt. And 1 picowatt is detectable. That is possible. And this is how you can hear a signal from the moon, your own signal. And if the computer, or if the presentation doesn't crash, because it did it several times, because this file is so big, that's a reflection from the moon. And that's on the 2-meter band. And here very closely, this is Morse code. Okay, should be sufficient to demonstrate what the effect is. Morse code is a binary transmission because the power goes out and that's it. There is no modulation on it. So the energy level of the signal rises instantly and it terminates instantly. But since signals come here at the nearest point of the moon and they're reflected a little further, there is a time delay. And even further down here, maybe there is a mountain. It will also be reflected. This means that those sharp edges come out in the end. Well, there is a three-second delay anyway, but let's project it onto it, like this. And at the end, it's like the effect from a capacitor. It will be delayed a little, and the signal is not so well detectable anymore. There are people who do voice transmissions also over the moon, and that's kind of the problem why they're very, very hard to understand. And that's also the reason why many people prefer telegraphy over the moon, because the signals are much easier to detect. As you could hear, you could very clearly distinguish, okay, there is a tone and there is no more tone. And if you can do that, older amateurs in Germany, it's no longer required to pass the telegraphy test. I did it, and I can just read that. It's like somebody's talking to me. I can just listen to that. It's just a matter of training. Okay, what's up with my presentation? LibreOffice is kind of weird sometimes. So, I think I have to continue this way. Oh, that doesn't work. Okay. Well, you can see the sky. Morse code is something that can make a lot of fun if you have learned how to write it and listen to it. But there are better ways to do it. And the person who's depicted here, that's Joe Taylor, a Nobel Prize winner, a radio astronomer who used to work at the MIT. And he did a lot of research on pulsars. And when he retired at the age of 65, he decided, well, he was an amateur radio operator, K1JT. He decided that he wanted to do something in amateur radio with the background knowledge of his profession. And he wrote a program, the WSJT. And the WSJT program was designed for moonbound transmissions. It's called Weak Signal Communications by K1JT. The WSJT has a number of derivatives for all sorts of applications, not just for moonbounds, but also for shortwave transmissions. One of those applications will be presented afterwards by Michael. That's also a way to use or a way to analyze very low energy signals. Here, the signal in this case consists of 65 tones. There's one lead tone, one synchronization tone, and 64 tones for transporting information. And the way how to do that is you connect a receiver to the computer through the sound card. In this case, it's not like this. I'm not going to talk depictively about this because this is really a fantastic device, but technologically, after all, this is something like a sound card, a very, very fast sound card. And in this case, WSJT does something similar. It takes the input from the sound card and does a lot of transformations, particularly the fast Fourier transformation, by which it can analyze signals way or much weaker than the background noise, and that's the interesting part about it. It also the transmission also relies on a fixed format. Well, depending on the modes, there are different modes, but here in this case, the first version relies on a fixed format, and it also has a very slow baud rate, just 2 baud. You'll see that in the next slide, one of the next slides. A more or less precise PC clock is also required, and one transmission can transfer 13 characters. It's not very much, but given that you transmit it over 800,000 kilometers, this is quite interesting nevertheless. What's in the standard transmission? Your call sign, or the call sign of the sender. A report in dBm, it's not dB, it's dBm, how strong the signal is. So when I'm sending, I tell all the others, okay, my signal is 10 milliwatts. And my locator, so where I am located. And the receiver can then say, okay, the signal goes from here over the moon to there. Here is a screenshot how it looks like. Maybe it's, no, it has not recovered in the meantime. Wait a moment, please. Let's do it the hard way. Is it this one? No, next one. Okay, restart. That should be okay. Let's try it again. I hope it doesn't crash again. Yeah, some technical problems ahead.
Try by deleting the slides before the one you want to complete.
Yeah. Well, the mistake was to embed the sound file in the presentation. This is probably something you shouldn't do if it's very big. Okay, here we go. Well, now I'm just jumping to this slide here and hope to make it a little bigger. Then you can read that. These figures are very small here, but they're the most interesting ones. You see the JT65A mode here has a baud rate of 2.69, and the SNR is minus 25. And that's the interesting thing. You can detect a signal that is as weak as 25 decibel below noise. And that's really, really fantastic. And unfortunately, I've not yet seen a re-implementation of WSJT in GNU Radio, which should be possible because it's open source. You can download and compile it yourself. And that would be something really fantastic. And if somebody of you can implement that, I would be very, very happy. So, those of you who already have a call sign don't need to worry about that. But for the others, I have good news because there are lots of frequencies which you can use. Amateur radio frequencies start from 135 kilohertz and go up to, doesn't start here, way beyond 250 gigahertz. So you can play in all of those frequency ranges, and it goes from kilometer waves to millimeter waves, and you have all sorts of funny things which you can play with which you can play around. You probably don't believe what's there that reflects. Everything reflects. It's incredible. Just recently I heard an example that somebody is doing rain reflections. I mean, of course, all of you know there is a rain radar in the internet, so rain reflects radio signals. And you can send a signal into a rain cloud, which is 10,000 meters high, and it will reflect far beyond the horizon. You can talk to other people through a rain cloud. It's possible. That's a real cloud application. Something else that's very funny, of course, you can use airplanes to talk over them. You send a signal to an airplane, and the airplane will reflect it far beyond the horizon, because the airplane is also 10,000 kilometers up. And you can talk to other people through a reflection on an airplane. There are applications how to do that. People do that. And this is why I tell you that amateur radio is a lot of fun. It's a playground for curious people. And if you have questions how to do that, there are people who know how to do it. In almost every country there is a radio club. In Germany we have the DARC, Deutsche Amateur Radio Club. Here in Belgium we have the UBA. And contact them, they will tell you how to get a license, and it's not so difficult. Since you're sitting here and you're interested in radio, it should be easy for you to pass the license exam. It's not so difficult. I did it when I was 14 years old. So everybody of you can do that. Right, thank you very much. If you have any questions. Any questions? To count birds? I haven't, but why not? Should be possible. They do reflect for sure. Okay, thank you very much.